In this video I'm going to demonstrate what I have recently discovered, which I think is a big breakthrough for me at least, to be able to physically demonstrate and physically identify the effect of EPR, or Electron Paramagnetic Resonance, which is closely tied to Dynamic Nuclear Polarization, which is something that I've been working on and off over the last number of months. So I just want to demonstrate that it seems pretty obvious that I've actually been able to do this, and it creates motion in a number of different materials. This is one of them. A few different things I've been testing. What I found is it's very dependent on frequency. I was able to dial it in to fractions of a hertz. This is in the 58 megahertz neighborhood. And for this coil that I've made, the associated magnetic field necessary for that to excite Larmor precession in the electrons in these different materials, in the unpaired electrons. So I'm running about 0.360. Oh, actually I do have the magnetic field on, which I didn't mean to do that. Okay, so the RF is off, magnetic field is off. What I'm going to do is turn on the RF, and you'll see this needle deflect here in pulses, and that's showing that the RF is turning on and off at that frequency. So I'll turn it on here, and what I want to do is just show that the RF alone will not make any significant forces on this cup with this powder in here. I try to time this on-off frequency to match the natural frequency of this pendulum here, because that's what this is a pendulum. So I can increase the swing. So as you can see there's no really discernible, noticeable motion. But when I turn on the magnetic field, which, by the way, the reason that this big coil is like this is it's a big solenoid. So solenoids are known to have a very uniform magnetic field through the middle, and that's the goal, is to have a uniform field where the magnetic field is as constant as possible at any given point. So I got to turn this up to about 0.36. Right about there, and it takes a moment for the capacitors to charge up and all that. So I'll just put this back here. You'll start to see, hopefully on the camera, you'll start to see this cup will start moving a bit. So 0.355 amps. Got to go a little higher. I'm turning these knobs very carefully. Once I hit resonance, you'll start to see that cup moving. It won't be a lot, but it should be noticeable. I can see it with my eyes. me just dial it in a little better here. It's very specific. Like, it's definitely a property of resonance. Which is what EPR and NMR and DNP, all these different techniques are about. Larmor precession, which is basically a resonant frequency. There seems to be a little bit of hysteresis too with the magnetic field. Like, the sample will store, it seems like it kind of stores the magnetic polarization to some degree. So it's moving a bit there. I know you guys are going to say this is air currents and stuff like that, but it's not about air currents, because I've done this numerous times. It's just a little hard to get on video. It's also more ideal to tune it with the function generator than to tune it with the DC power supply, because it doesn't have as much resolution. So it's a little trickier to nail the resonant frequency. I'll try a different sample. So there's a different sample material, and there's some green tape on there just to help with visibility. Field will be at 0 right now, and the RF is off. So what I'm going to do is turn on the RF first. Just to show that, to rule out any kind of like radiation pressure ideas. Okay, so as you can see, it's just about perfectly still, not moving around by air currents, okay? So I'm going to turn on the RF right now, pulsing it again at about half a hertz. Okay, I'm going to zoom in here. I'm going to keep our eyes on that. Okay, now I'm going to turn on the magnetic field. Um, 200. 250 milliamps, 300, and just about there. It says 360 milliamps. It's moving around a little bit, the readings, so it's, I don't know how precise it is. Now you should be able to start seeing this puck move just a little bit. I'll try to tune it a bit better. There's a real sweet spot, and it's difficult to get, but it is doable, and that's what I want to share in this video, that it is doable, and there is a definite force or physical motion as a result of this resonance, and I think that could be significant for propulsion. And so there could be some, as far as Fred Alzofon's theory goes, there could be some validity to that, and Todd Desiato's theory. But I got to do more work with this, and I'm going to flip the coils around to see if I can get lift or, you know, anti-gravity out of it. That's yet to be seen. So right now it could be repulsion between the precessing electrons in the cobalt atoms and the field in this coil. But as far as like nuclear polarization and how that relates to gravity is still, I'm still working on that. So there's a tiny bit of motion there. See if I can dial it in a bit better. And just by the way, I did try like polycarbonate plastic. Didn't work very well. It was hardly noticeable. Bismuth, this big bismuth plate, I could get to move a little bit, but I'm finding bismuth is, because of its diamagnetism, doesn't work that well. So it should work with any material with like that's like paramagnetic. It's to do with unpaired electron spins. Anyways, just wanted to share that. This is a good thing, and yeah, thanks for watching.